Hello and welcome to another video of Grokking the Coding Interview Series. We are going through the depth first search pattern, and in this video we'll have a look at some of path numbers, which is classified as a medium problem. So let's read into the question and try to understand what is being expected of us given a binary tree where each node can only have a digit 0 to 9. So this restriction is important. The digit can only be from 0 to 9. Each root to leaf path will represent a number. For example, 1 to 7 will represent 17, 192 will represent 192, and so on. Find the total sum of the numbers represented by all the paths. So essentially, we have to sum all these numbers and provide a final output, which will be the overall summation across these paths in the tree. So one of the of course, one of the assumptions which is important is that this digit can only be from 0 to 9. And one of the tricks which we need to know in order to solve this problem, of course, you could go ahead and solve it another way as well, where you just go and keep a track of all the nodes, and then you can have some sort of join statement on that. Representing each as string, and then you can cast it as an int, and then you can go ahead and add that. However, it would mean that you have to maintain a list of all the nodes in the path, and in the end go ahead and sum it. But what we want to do is we want to keep a track of running sum, so we do not have to store all the nodes in the current path. And the way we can do it is, say if we want to represent a number, say incrementally, so what it would essentially mean at a specific node, the say at a specific node, for example, if we are at node 7, it would represent number 17. So how can we do that? So essentially what we do here is we say the path sum here will be 1 times 10 plus the value of the current node. So for example, if we wanted to get the path sum here, it will be 9 times 10, or hold on. If we wanted to get the path sum at this node here, so we already have a path sum as at this node, which will be 10 plus 9, and then we have 19 times 10, which is 390, and then we'll add 9 into it. So at every subsequent node, we have to multiply the previous node sum by 10 and add the value of the current node in it. So let's do that exercise for this number again. So here the sum will be 1. As soon as we move here, it will be 1 times 10 plus 9, which will be 19. As we move here, it will be 19 times 10, which will be 190, and we'll add 2 into it, so it will be 192. So you see how we keep a track of the running sum, and as soon as we encounter a leaf node, we simply go ahead and return that sum, and we just simply have to add these values for both the left. So at this stage, if we want sum of all the branches, we simply have to add the path sums for the left subtree traversal and the right subtree traversal as well, and this would give us the answer which we are looking for. So let's quickly go ahead and see how we can go about implementing a solution here. Again, the structure of these recursive calls will remain the same. We'll have one invoking function and one function in which we'll run our recursion as such. So let's do this recursion here. We just append, and we provide the root. We provide the current sum or the running sum, which will be 0. We have this here. We have current node and say running, or let's say path sum. If current node is none, we simply return 0, as the path sum in that case will be 0. And we calculate the path sum for this node, which will be, as we spoke about it, 10 times the path sum, and we add the value of the current node. And at this stage, we want to check if current node dot left is none and current node dot right is none. If this is the case, we have encountered a leaf node, and we'll simply return the path sum. Otherwise, we'll keep on traversing, and our traversal will be focused on the left subtree. So current node left, and what will we provide as running sum? This will be the path sum, and we'll add. We want another one of these here. The current node dot right and path sum again. So this should actually give us the answer which we are looking for. Let's see which example are we actually providing here. 165. Okay, so this is the example which we are providing, and the answer we are expecting is 332. Okay, let's try to run it and see if we have the answer which we are expecting. Okay, okay, I'm not sure why that is not working, but let's then just put it up here for now. Okay, so it seems like our implementation is working. Again, the trick here, as we went through that, it was we are calculating the branch sum, running branch sum as we are traversing the node instead of first traversing, then joining all those numbers and casting it into an int, and then calculating the sum. Uh, and that makes everything much more efficient. So let's speak about the runtime and space complexity of this algorithm. So when it comes to runtime complexity, we are essentially it'll be O of n as we are traversing n nodes. Okay, so it'll be O of n, and when it comes to the space complexity, it'll be O of n in the worst case, and that case will be when the given tree is a linked list. So again, I think these are the components which are important to remember, because it wouldn't be as intuitive right away. But if we have been solving similar problems, we've been countering this reasoning. So the worst case scenario for a tree can be, in terms of space, can be when it is a linked list, and it'll be often. Okay, great. I hope you found the explanation clear. Please let me know if something was not clear. More than happy to address it and improve on that. Until the next video, have a great day. We'll be covering all these problems in the next video. So have fun, enjoy your day.